Welcome to this presentation. In this presentation, I am going to speak about the satellite communication and satellite orbits. The use of satellites in communication systems is very much a fact of everyday life, as is evidenced by the many homes equipped with antennas or dishes used for reception of satellite television. And what may not be so well known is that satellites form an essential part of telecommunication system worldwide, carrying a large amount of data and telephone traffic in addition to television signals. Satellites offer a number of features not readily available with other means of communication because very large area of the earth are visible from a satellite, and the satellite can form the start point of the communication net, simultaneously linking many users who may widely be separated geographically. The same feature enables satellites to provide communication links to remote communities in sparsely populated areas that are difficult to access by other means. Of course, satellite signals ignore political boundaries as well as geographic ones, which may or may not be a desirable feature. Now, let us discuss about the basic Kepler's law. Actually, the satellite is nothing but a body which orbits around another body in space. There are two different types of satellites called natural and man made. Examples of natural satellites are Earth and Moon. The Earth rotates around the Sun and the Moon rotates around the Earth. A man made satellite is a mission that is launched into the space and orbits around a body in a space. Examples of man made satellites are Sputnik, Aryabhatta, GSAT, and so on. The world's first artificial satellite, the Sputnik 1, was launched by Soviet Union on October 4, 1957. Sputnik 2 was launched on November 3, 1957, and the United States launched their first satellite called Explorer 1 on January 31, 1958. Aryabhatta was the first unmanned Earth satellite built by India, assembled at Penya near Bangalore, but launched from the near by a Russian-made rocket in 1975. So what you see here is frequency bands used for satellite services. So the frequency ranges are from 0.1 to 0.3 gigahertz are used in VHF, whereas 0.3 to 1 is used in UHF and so on. You can see the various frequency ranges and the band designation here. And now let us see the basic Kepler's laws. John Kepler derived Kepler's laws. Kepler's laws apply quite generally to any two bodies in space which interact through gravitation. The more massive of the two bodies is referred to as the primary and the other the secondary of satellite. And Kepler's first law states that the path followed by a satellite around the primary will be an ellipse. An ellipse has two focal points F1 and F2, which is shown in this slide. So these are the focal points F1 and F2. The center of the mass of the two body systems, termed as the barycenter, is always centered on one of the foci. In our specific case, because of the enormous difference between the masses of the Earth and the satellite, the center of mass coincides with the center of the Earth, which is therefore always at one of the foci. So here you can see the major axis and the minor axis, and the center of the ellipse is shown here, and the semi-major axis is denoted by A, and semi-minor axis is denoted by B. Right. The semi-major axis, as I said earlier, is denoted by A and semi-minor axis as B. Then the eccentricity is given by E is equal to square root of A squared minus B squared by A. The eccentricity and the semi-major axis are the two of the orbital parameters specified for satellites orbiting the Earth. For an elliptical orbit, 0 less than E less than 1, then when E is equal to 0, the orbit becomes circular, And the geometrical significance of eccentricity along with the some of the other geometrical properties of the ellipse will be developed. So, for an elliptical orbit, E will be equal to 1, for a circular orbit, E will be equal to 0 here. And Kepler's second law states that for equal time intervals, a satellite will sweep out equal areas in its orbit plane focused at the barycenter. So, you can refer this figure. So, assuming that the satellite travels a distance s1 and s2 meters in 1 second, then the areas a1 and a2 will be equal. So, the average velocity in each case is s1 and s2 meter per second, and because of the equal area law, it follows that the velocity at s2 is less than that at s1. So, an important consequence of this is that satellite takes longer to travel a given distance when it is farther away from the earth. Use is made of this property to increase the length of the time of a satellite that can be seen from a particular geographic regions of the earth. This is what Kepler's second law states. And now let us move on to Kepler's third law. So Kepler's third law states that the square of the periodic time of the orbit is proportional to the cube of the mean distance between the two bodies. So the mean distance is equal to the semi-major axis A. For the artificial satellites orbiting the Earth, Kepler's third law can be written in the form A cube is equal to mu by n square. So where n is the mean motion of the satellite in radians per second and mu is the Earth's geocentric gravitational constant, and its value is mu is equal to 3.986005 into 10 power 14 meter cube per square. Okay. So this equation applies only to ideal situation of the satellite orbiting in a perfectly spherical Earth of the uniform mass with no perturbing forces acting such as atmospheric drag. So the effects of the Earth's oblateness and atmospheric drag will have to be taken into account. So with the n in radians per second, the orbital period is given by p is equal to 2 pi by n. The importance of the Kepler's third law is that it shows there is a fixed relationship between period and semi-major axis. One very important orbit in particular, known as the geostationary orbit, is determined by the rotational period of the Earth. So in anticipation of this, the approximate radius of the geostationary orbit is determined by equating that as p is equal to 2 pi by n. So this equation applies only to ideal situation of a satellite orbiting to a perfectly spherical Earth of uniform mass with no perturbing forces acting such as atmospheric drag. Okay. So now let us take an example how to calculate the radius of the orbit. Okay. So what is given here is we have to calculate the radius of the circular orbit for which the period is 1 day. So they have given the period as 1 day, and if you convert it into seconds, it will be 86,400 seconds. So when you convert it into hours, minutes and seconds. Okay. And therefore we can calculate the mean motion as n is equal to 2 pi by p. Therefore n is equal to 2 by 86,400, which will give you a value of 7.272 into 10 power minus 5 seconds. So from Kepler's third law, A is equal to 3.986005 into 10 power 14, that is mu, divided by this n value 7.272 into 10 power minus 5 the whole square whole power 1 by 3. So if you calculate this value, you will get the value of 42,241 kilometers. So since the orbit is circular, the semi-major axis is also the radius here. Now let us have a look into Newton's laws. Newton's first law states that if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon a force. So Newton's second law states that if a force F works on a body of mass m and acceleration a, then F is given by F is equal to ma. And according to Newton's third law, when two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. If one body exerts a force on a second body, the second body exerts an equal and opposite force on the first. And now let us see the Newton's universal law of gravitation. The universal law of gravitation is usually stated as an equation, that is F is equal to gm1 m2 divided by r square. That is, the attractive force that occurs between two masses is denoted by F. So, and G is the universal constant of gravitation, and usually G is equal to 6.67 into 10 power minus 11. And m1 and m2 are the masses of the two objects which are separated by a distance r. Thank you.